This assignment is to analyze and test a proposed design for a temperature measurement subsystem, which will be included in a simple temperature control system. The report you create will convey the results of this analysis to another group on the team. First, I'll introduce the background of this engineering assignment and place this task in the context of the overall project's goals. After that, I'll introduce the preliminary design for the temperature measurement system that you're going to analyze and some governing equations that may help when you analyze the system. Finally, I'll demonstrate how I acquired the data that you will use when doing your analysis and writing your report. Your job will be to use the data and analysis methods presented in this video to draw conclusions and transmit those conclusions to another group through an engineering report. First, some background information about the overall project. This is a block diagram showing the anticipated structure of the control system. The goal of the system is to maintain the temperature of some mass at a desired value. You can think of this as anything whose temperature is important, such as a hot plate that your coffee cup sits on. In that example, you want to keep the hot plate at a temperature that makes your coffee pleasant to drink. The input to the control system is some desired temperature. In our hot plate example, you would increase this number to make your coffee warmer and decrease it to let it cool down. This temperature is, as is most information, represented by a voltage. There's another subsystem here which measures the temperature of the mass, or the hot plate in our coffee-related example. This is the block of the system that you'll be responsible for in this project. This is what is called a feedback loop. The measured temperature, represented by a voltage, is fed back and compared with the desired temperature. The controller here takes this comparison and decides how much heat to apply to the mass to keep it at the desired temperature. This approach can be as simple as just comparing the actual temperature and the desired temperatures and either turning a heater on or off, depending on which is higher. You turn off the heater if the mass is too warm, and you turn on the heater if the mass is too cool. This would be a typical approach for a home heating system, for example. In the scenario I've set up for this project, the group in charge of the controller needs a mathematical model of the measurement system in order to simulate the overall system and design this controller. We'll model the measurement system as some amount of voltage change at the output of the measurement system per degree of change of temperature of the mass. Our job is strictly related to the temperature measurement subsystem. The temperature measurement system needs to convert a temperature to a voltage. We want the output voltage of our temperature measurement system to be proportional to the temperature itself. Basically, we want there to be a single number that we can multiply a temperature change by to get the corresponding voltage change. The number will have degrees of volts per degree of temperature. This proportionality constant is called the sensitivity. The built-in assumption when we model the system as a single number, a sensitivity, is that when we plot the output voltage as a function of the temperature, we'll get a straight line. When we look at our data later, it will probably turn out that there is not exactly a linear relationship between temperature and voltage, which would mean that the sensitivity isn't really just a single number. To represent sensitivity as a single number, we'll have to choose a linear relation that does as good of a job as possible of modeling the actual system behavior. In this assignment, you already have a preliminary design for the temperature measurement system. Your responsibility is to analyze and test the design to ensure that it works and estimate the sensitivity of the design. Any instrumentation system requires a sensor. The sensor is a specific type of a more general group of devices called transducers, which convert different types of energy. For example, a pump is a transducer that uses electrical energy to pump water uphill. The thermistor converts heat energy or temperature to resistance. You can then use that resistance change to get a voltage. In the technical parlance, our thermistor is specified as an NTC 10 kiloohm at 25 degrees C thermistor. NTC means negative temperature coefficient, which just means that the thermistor's resistance decreases as temperature increases. The rest of the notation just means that the resistance at 25 degrees C should be around 10 kiloohms. In fact, a typical resistance versus temperature characteristic for our thermistor looks like this. However, you'll have to test the thermistor to determine how it really behaves. Our sensor gives a resistance change if you change its temperature. You need to convert that resistance change to a voltage change. The preliminary design we've been given is to use a fixed 10 kilo ohm resistor in series with the thermistor to form a voltage divider. For this circuit, the output voltage, which is the voltage across the 10 kilo ohm resistor, is given by V out is equal to the supply voltage, V sub S, times 10 kilo ohms over 10 kilo ohms plus RTH. So, as the temperature increases, the thermistor resistance decreases and the output voltage goes up. This relationship will probably not be linear, but you'll have to approximate it as a linear relation as best you can once you do your analysis and analyze the data. Here's my recommended plan of action for doing the analysis and data reduction necessary to write your report. First, you need to characterize the thermistor. You need to measure the resistance as a function of temperature. I'll do that part for you, and in the next section of this video, I'll show you how I acquired the data. The data will be available on the website. Secondly, you'll want to mathematically predict the behavior of the temperature measurement system, which was the voltage divider on the previous slide. The ability to predict the behavior of the system and compare your expectations to the data is very important. You may not need this information to determine the sensitivity, but if a redesign of the system ever becomes necessary, this is the tool that you'll need to be able to do that. Next, you build the temperature measurement system and measure its output voltage over a range of temperatures. I'll also do this part for you. The data will be available on the website, and in the last part of this video, I'll demonstrate how I acquired the data. Finally, you need to use the information you have to estimate a sensitivity for the system. This will require you to fit a straight line to the temperature versus output voltage data that was acquired in part 3. There are some MATLAB tutorials available on the website that will help you do that, or you can use Excel if you prefer. The slope of the line approximating the data will be the number you need to give to the control group. Now, let's demonstrate the data acquisition for this assignment. This is the thermistor we're going to be using. The resistance between these two leads changes as the temperature of this disc changes. For our test setup, I've taped a thermistor to a kitchen thermometer so that I can monitor the temperature as the resistance changes. The resistance is being measured by this DMM across these two leads. If I immerse this in hot water, the resistance is very low. Now, as the water cools down, this resistance will increase. Now, after a while, the water's cooled off, this resistance is starting to climb. As it continues to cool, the resistance continues to rise. Now, the overall system includes a 6-volt power supply. The positive terminal of this power supply goes to the thermistor that we're changing the temperature of. The thermistor connects through this wire to our fixed resistor. The other terminal of this resistor is connected to the negative terminal of my power supply. My DMM is set up as a voltmeter to measure the voltage across the fixed resistor. When the temperature is high, I get a relatively high voltage reading. As the temperature of the water decreases, the voltage level goes down. And as the water temperature continues to go down, the voltage gets lower and lower.